Okay, we are in section 4.3. 4.3 talks about linearly independent sets or bases. Okay, so this is a very important section, of course. And you learned about linearly independence back in section 1.7. So let's review what is linear independence. If you have a set of vectors that are linearly independent, this means then if you take a linear combination of those vectors and set them equal to the zero vector, the only linear combination that will solve that vector equation is if all the coefficients equal zero. Okay, that's the idea of linear independence. If it's not such the case, then you have a linear dependence relationship. Okay. So you have, I mean, a nice way of thinking about linear dependence is this theorem 4. Okay, and theorem 4 here, it says if you have a set of two or more vectors, they're linearly dependent if and only if for some vector in the set, it's a linear combination of the preceding vectors. Okay, so like an example of this, let me go to the whiteboard. Okay, so let's say you have a vector v1 that's 1, 0, 0. And then you have a vector v2 that's 0, 1, 0. Okay, and then you have a vector v3 that's 0, 1, 0, 0, 1. Now, so far, is this set of vectors linearly independent or dependent? And these, remember, these vectors here, these vectors are unit vectors that lie on the x1, x2, x3 axis. All right, those are independent. Okay, now notice that the vectors live in three-dimensional space. Okay, so if I were to say, define H to be, let me be even more clear here. Let me be more clear. This is fine what we have, but let me just write something else here. Hold on. I mean, I'm going to keep what I had, but let's say the space H is the span of, like I said, the vectors 1, 0, 0. That's v1. 0, 1, 0. That's v2. And v3 is 0, 0, 1. Now, space H, okay, is in R what? Space H is in R Let me make this a little easier. Let me take out the third vector. Okay. Let's say this is your space here. Let's say this is your space. Okay. H is a subspace. And why is it a subspace, class? Why is H a subspace? How do we know H is a subspace? Don't even have to confirm the properties, right? Why is that? Well, H is the span of a set of vectors, right? Anytime you have the span of a set of vectors, you have a subspace. But H is a subspace of what space? Where does this space H live? Does it live in two-dimensional space, three-dimensional space, four-dimensional space? H is a subspace of R. Well, H, Yasin, H is a two-dimensional. It's a two-dimensional subspace of R. Where do the vectors live? How many entries in each vector? If you were to graph the vectors, where would you graph them? Would you graph them in R2 or R3? R3, right. That's right. But of course, the span of that vectors, this is a plane, right? This is a plane. Okay, it's actually the x1, x2 plane. All right, that's what geometrically that span is. And are these vectors linearly independent? Are v1 and v2 linearly independent? They are. They are linearly independent, absolutely. Now let's do another space here. Let's say H, or the span. Well, no. All right, so, all right, well, it's good we did that. It's good we did this. But let's say you had this set of vectors. Really what I want to do is justify theorem 4 in section 4.3. So I'm going to put 1, 0, 0, 0, 1, 0. So far, are my vectors linearly independent? 1, 0, 0, and 0, 1, 0. Yes, so far they're linearly independent. Okay, I'm trying to make things look good here. Okay, let me add another vector. 0, 0, 1. So far, are the vectors linearly independent? They are. If we have, that's right, Justin. If we have V1, V2, and V3 here, they're linearly independent. Now let me add a fourth vector. I'll call it 1, 2, 3. I'll call that V4. Is this set here now, these four vectors, is that a linearly independent set? V1, V2, V3, V4? No, that's right, it's not, because V4 is equal to 1 times V1 plus 2 times V2 plus 3 times V3. In other words, V4 is a linear combination of the preceding vectors. So anytime you have a set, a linearly independent set, one of the vectors has to be a linear combination of the preceding vectors. It could, and eventually that has to be true. Okay, it just has to be true eventually. So we're very interested in section 4.3. We're very interested. Hold on, where'd my, one moment. Let me get my book here, one moment. Thank you for your patience. There we go. So what we just showed here was we demonstrated theorem 4. Okay, if you have a linearly independent set of vectors, at some point, I mean, one of the vectors will have to be a linear combination of the preceding vectors. Okay, it just has to be that way. Now, let's talk about what a basis is. Let's talk about what a basis is. So we're reviewing what linear independence means. Okay. And I guess it doesn't hurt to look at this first example. Why not? Hold on here. Let me see. One moment, class. Yeah. So here you have polynomial vectors in example 1. Polynomials. Well, this set of polynomials is linearly independent because in the space, in the polynomial space, because the third polynomial is a linear combination of the first two polynomials. Okay, so a basis. Definition of a basis. So an index set of vectors is a basis for the vectors for the space H, the subspace H, if the collection of vectors is linearly independent set, and if the space spanned by that set of vectors coincides with H. Okay. So, like for example, if we go back to the whiteboard here, hold on here, get this crazy thing off here. I don't know why it's doing this. Don't give me that. Okay. Thank you. Okay. So let's say, you know, well, hold on. Okay, so, you know, E1 is 1, 0, 0. E2 is 0, 1, 0. And E3 is 0, 0, 1. Those are the standard unit vectors. You're used to calling them I, J, and K. And is R3 equal to the span of E1, E2, and E3? Definitely it is. Definitely it is. That's right, Mikhail. And further, we know that this set of vectors, Any vector in R3 can be written as a linear combination of those unit vectors. And further, we know those unit vectors, we know they form a linearly independent set. So therefore, that set of vectors is a basis for R3. Okay. So really what we did here in the definition of a basis, this was really condition 1. I listed it second, and this is condition 2 at the top. But the fact that conditions 1 and 2 are satisfied means that this set of vectors is a basis for R cubed. And it's actually, in this case, it's what's called the standard basis. Because it's like the easiest basis. We can take any vector in R3 and write it as a linear combination of E1, E2, and E3. Like, for example, if you take the vector, take the vector 1, -5, and 4. 1, -5, and 4 would equal something E1 plus, this is section 4.3, yep, something E2 plus something E3. We're in section 4.3 now. So what numbers are going to go here? It's okay, no problem. What numbers are going to go here? Good. 1, -5, and 4. Any vector in R3 can be written as a linear combination of those vectors. Very easy to see. That's why we call that a standard basis. Are there any questions so far? Who's feeling comfortable? Maybe give me a thumbs up if you're doing okay. Yeson's good. Marcella's good. Cameron's good. Wonderful. Wonderful. All right. Well, let's now look at an example in the book of another basis for R3. So if we go back to the book here, and look at example 5. Sorry, let me bring it up here. I got to bring it up, don't I? By the way, in figure 1, there's the picture of the standard basis for R3. Well, you see, Mikhail, you can have an infinite number of bases. Here's like example 5. Okay, example 5 here. They say, okay, let V1 be the vector 3, 0, -6. Let V2 be the vector -4, 1, 7. And let V3 be the vector -2, 1, 5. Determine if the set of vectors V1, V2, V3 is a basis for R cubed. What do we need to determine if we have a basis? We have to determine if the set of vectors is a linearly independent set, and we have to determine if the span of those vectors is equal to R3. Okay. Well, in the solution, how do they determine if it's a basis? if we look at the solution, it says, well, there's several ways to choose to do it, but one is you can set up a matrix, okay, with column vectors v1, v2, v3. And if that matrix, say, is invertible, then by the invertible matrix theorem, the vectors are linearly independent. Now, what I'm doing is I'm going back to section 2.3, where that invertible matrix theorem is. And it says that if you have a matrix A that's invertible, that's in the theorem 8, invertible matrix theorem, section 2.3. If A is invertible, that implies then that then by, A, like there are a number of properties, but if A is invertible, that's like part A of the theorem, then that implies part E of the theorem. The columns of the matrix A form a linearly independent set. So you see what they do is they create the matrix A with the vectors v1, v2, v3, show that the matrix A is invertible. Then by the invertible matrix theorem, the vectors v1, v2, v3 are linearly independent. Okay, so now what you have is you have 3 linearly independent vectors in R3, and the span of those 3 vectors has to equal R3. Okay, if you have n-dimensional space, and you, in other words, let me just say it the right way. Let me go into the whiteboard again. Okay, so let's think about now span. This is relating to example 5 in the book. Span of 3, 0, negative 6. That's V1. And negative 4, 1, 7. That's V2. The span of the first 2 vectors is, can it be all of R3? The span of the vectors V1 and V2? Can it equal all of R3? No. The span of V1 and V2 would be a 2-dimensional subspace of R3. Okay, to get the 3-dimensional subspace, you have to add a 3rd vector. And if the 3rd vector is linearly independent from the first 2 vectors, then that span of those 3 vectors will equal R3. Okay, so we had a basis. In other words, this set here, 3, 0, negative 6, negative 4, 1, 7, and negative 2, 1, 5. This is a basis. This is a basis for R3. Just as is the basis 1, 0, 0, 0, 1, 0, and 0, 0, 1. That's also a basis for R3. Okay? So the key for the basis is the vectors have to be linearly independent, and they have to span the space. Okay, are there any questions on that? Essentially, a basis is it's an efficient, like, let me show you another example here. Let me show you another example. I think I have these examples in my mind that I think are very, very helpful to you. Hopefully they are. So the span of these three vectors equals R3, right? What's the span of these four vectors here? Equal to. So it still would be R3. That's right, Mikhail. It still would be R3. Okay. The linear combination of those four vectors would any vector in R3 could be written as a linear combination of those four vectors. Okay. And in fact, what would the linear combination be? Well, so it could be C1E1 plus C2E2 plus C3E3 plus 0 times that last vector, 1, 2, 3, right? See how that works? Yeah. The span, but which, let me separate this. Which is a basis? Which is a basis? E1, E2, E3? I mean, which forms a basis? The first or the second set of vectors? Which forms the basis? The first set or the second set of vectors? It's the first set. Because you only need these three vectors. Notice it's three-dimensional space and you have three vectors. You only need three vectors to form a basis for three-dimensional space. You don't need a fourth vector. The fourth vector is unnecessary. You only need three linearly independent vectors. If you add in a fourth vector, that fourth vector is going to be it's going to be a linear combination of the first three vectors, and you'll have a linearly dependent set. You won't have a basis anymore. So in a sense, a basis is an efficient spanning set. It's an efficient spanning set. You see what I'm saying? there any questions on that? Cameron's good? Okay. Let's do, all right, let's do an example. Let's do another example here. This one I have as part of the notes. At least I did, hold on. Yeah, let's look at this one. Let me give you a moment to copy this down, okay? This example. This is an example I made up to help you develop a good feel for this. Okay. Hold that thought, Mikhail. Hold that thought. So let me ask you this. Let me ask you this. If this problem said find a basis for the span of these vectors, let's say that you had this 1, 0, 0, 0, 1, 0, 0, 0, 1, and 1, 2, 3. Hold on, I got my font too big here. It always wants to use 5-point font. I don't know why it can't put it down to 3. I mean, you know, but it's okay. Let's say I were to say, hey, let's find a basis for this set here. I'll call it space K. And let's say space K is the span of these vectors. 1, 0, 0, 0, 1, 0, 0, 0, 1, and 1, 2, 3. What would the basis be for this set here, this set K? What would the basis be? So what I'm trying to say is this is separate from this example. Don't focus here. Pretend that you don't even see this for the moment. You don't see this for the moment. I'm saying if I said find a basis for this space K, which is the span of those 4 vectors, okay, the vectors, by the way, are E1, E2, E3, and then some vector V4. What would the basis be? What would the basis be? Tell me the vectors that are in the basis. That's right, Yasin. Excellent. E1, E2, and E3. So it's obvious by observation that the first 3 vectors are linearly independent, and you only need 3 vectors. They live in R3. You only need 3 vectors to span 3-dimensional space. Okay, so that would be your basis for this space K. And by the way, this space K is equal to R3, right? The span of those four vectors is just R3. What differs now in this situation is you have something where these four vectors, you can't judge easily what the linear independence relationship is between those four vectors. Is the basis just going to consist of the first two vectors? Would it consist of the first and fourth vector? Would it consist of three vectors? We know it's not going to consist of four vectors. It has to be, all right, Mikhail, well, we'll see if that's right. So, and Yasin, we'll see if that's right. We'll see if that's right. Hold that thought. So let's go ahead. We have to determine the linear dependence relationship between these four vectors. So what I do, we got to tie this. We're going to tie this into what you've learned. I create a matrix A here. I create a matrix A whose columns are those four vectors: 130, 102, 204, and 260. And what we can do is we can actually solve this vector equation here. Take the linear combination of the vectors and set it equal to the zero vector to examine the linear dependence relationship between the four vectors. So if we take this vector equation and write it as an augmented matrix, this is what you'd have. And then you can do row operations on that augmented matrix. Okay, so obviously I left work out here because I'm saying this augmented matrix is row equivalent to this matrix here. This augmented matrix here is in what form? What form is this augmented matrix in? Right, reduced row echelon form. So you see, if we get the matrix in reduced row echelon form, now we have these column vectors here: B1, B2, B3. That's a 0 there. Fascinating material here. And B4. And we'll call that then the matrix B, consisting of B1, B2, B3, B4. We'll call that matrix B. Okay, so matrix B consists of columns B1, B2, B3, and B4. Now, there's a very interesting idea here. Again, we are trying to determine a basis for our space H. Okay, and in order to determine the basis, we need to determine we need to be able to understand the linear dependence relationships between the column vectors, okay, in our set. Well, what we did here was we did we set up the matrix A, we defined a matrix A with those column vectors, and then we solved the vector equation. Okay, this vector equation here. And if we focus here, on the on this augmented matrix here, maybe I'll use green here. I mean, if we focus right here, note that if you take 2 times the vector b1 and subtract the vector b4, that's the 0 vector. Or b4, vector b4 is 2 times vector b1. Well, it turns out if we go up and look here at, in the matrix A, if we look at A4 here, and we look at A1, hey, A4 is 2 times A1, right? So we did row operations on this augmented matrix, but the row operations preserved the linear dependence relationships between in other words, the fact that in the reduced echelon form of the augmented matrix, the fact that the fact that the fourth column was twice the first column, that's also true for the original augmented matrix. The fourth column, A4, is twice the first column, A1. Now, similarly, you might notice here another dependence relationship. If you take twice the vector B2 and subtract B3, you get the 0 vector. So that means B3 is twice B2. And okay, well, here, if you look at the vector A3, it's twice A2, right? A3 is 2 times A2. So the dependence relationships between the column vectors of a matrix can be determined easily by reducing the matrix or the augmented matrix into reduced echelon form. It's easier to see the dependence relationships between the vectors of a reduced echelon form matrix. No, it's easier to see the linear dependence relationship between the column vectors of a reduced echelon form matrix than it is for just some random matrix with a number of column vectors. So you see, you're going to use row operations, okay, to determine if you have a basis or not. So how many for this space H, okay, let's see here. What vectors are needed to form a basis for our space H? In other words, if I go back here, here's our space H. Okay, here are the 4 vectors. Okay, A1, A2, A3, and A4. Okay, which vectors are needed to form a basis for that space H? We know not all four vectors. That's right, Mikhail. The first two vectors, A1 and A2. That's going to be a basis for space H. Because if you go back here to what we have here, and you can always blow this up, right? Magnify the screen. The fact is that here, the fact is that A4 is 2 times A1. So if you know what vector A1 is, A4 is or A1 is a half times A4. And A3 is 2 times A2. So the A4 depends on A1, vector A4 depends on vector A1, and vector A3 depends on vector, hold on, get this, hold on. Vector A3 depends on vector A2. In other words, if you know what vector A1 is, you know what vector A4 is. If you know what vector A2 is, you know what vector A3 is. So you only need vectors A1 and A2. Okay. So this means that the set of vectors A1, A2 is a basis for this space H. Now let me ask you another question. Is the span of the vectors B1 and B2 equal to the span of the vectors A1 and A2? In other words, let me go here to the whiteboard. I'm going to let you copy this, don't worry. But so that's right, Mikhail. That's right. Here's B1 and B2. B1 was 1, 0, 0. B1 is 0, 1, 0. So those two vectors, the span of those two vectors is going to be the x1, x2 plane. But if you have the vectors A1 and A2, A1 and A2 is 1, 3, 0. And vector A2 is 1, 0, 2. Okay, so those two vectors, the span of A1 and A2, it's gonna, I mean, it'll be a plane, but it's not gonna look like this plane here. The span of the B1, B2 vectors is gonna be a plane like the horizontal plane, X1, X2 plane. The span of A1 and A2 vectors are not gonna be that plane. So you can't say that the spans of those of the vectors B1 and B2 equals the span of the vectors A1 and A2, but the fact that B1 and B2 form a linearly independent set, the first two vectors of that matrix B form a linearly independent set. The matrix B is reduced echelon form of matrix A. That means that the first two vectors of the matrix A also form a linearly independent set and a basis for, you know, the space. So that being said, let me go back to the thing here because I want us to finish this here. Hold on, where are we at here? Yeah, this is where we were. So, of course, the span of vectors b1 and b2 is not the same as the span of vectors a1 and a2. But we have shown that the vectors a1 and a2 form a basis, because that set of vectors meets the qualifications. Now, the span of the vectors a1 and a2 is actually equal to space h. Space h, remember, was all linear combinations of a1, a2, and a3, right? That's what space h was here. So if V is in the span of A1, A2, A3, and A4, then V can be written as a linear combination of those four vectors. Let me give you a moment to catch up here. Okay, so let me just add something in here. So the vector 2, 0, 4, this vector here, the same as 2. It's the same as 2 times a vector 1, 0, 2. Had to kind of get that in light. But the point is, if you take a vector v, okay, that's in space h, it can be written as a linear combination of those four vectors, a1, a2, a3, and a4. But you can write that linear combination so that you have a linear combination of the vectors here. You can write that. Hold on, let me adjust this. You can write that vector v then so that it's a linear combination of vectors a1 and a2, which is in the span of a1 and a2. So I just want to I wanted to show you, to really get into the details with a nice example. I hope this is helping you sort of understand these concepts. I hope it is. Is it? Okay, it's helping you, Cameron. Wonderful, wonderful. Sometimes to convince yourself of ideas, you have to come up with little examples that help convince you. Yeah, that's right. If we have an example that that just sort of a nice clarifying example, it reinforces the theory. Okay, so this is really a lot of what section, it's really basically section 4.3. We basically covered it pretty well. The only thing we hadn't talked about yet is a basis for the null space of a matrix, but that's not a hard thing to understand. If you you'll be fine on that. You'll be fine on that. So the basis for the null space of a matrix, if you write the null space of a matrix in terms of its spanning set of vectors, you can take a null space and write the null space in parametric vector form. The vectors that are in the parametric vector form will form the basis for the null space because they're going to be linearly independent. Okay. And because the null space is the span of those vectors. So, are there any questions on section 4.3? Give me a thumbs up if you're feeling at least. I mean, I know you got to practice, but are you all right? Cameron's feeling reasonably okay. Mikhail's good. Marcella and Yasin, wonderful, wonderful. I'm very glad to hear it. Very glad to hear it. Belen, excellent, excellent. That's what I want to hear. That's what I want to hear. All right, let me stop the recording here then. Just see here. I think we have hit this example pretty well. Yep. Excellent. Excellent.